Over the last several lectures, we've encountered a number of interesting random times associated to certain Markov chains. The hitting times, return times, passage times of given sets or states. In many cases, we were able to compute or at least say very meaningful things about the probabilities of those times being finite or their expected values. And one reason that there were natural tools for analyzing those times is that there are no random times. They had specific structure. We're going to spend the next several lectures exploring that structure now. These were examples of stopping times. A non-negative or infinite integer-valued random variable is called a discrete stopping time if, for each n, the event that time is less than or equal to n can be decided with information that you have only up to time n. That is, that's an event in the nth sigma field in the filtration. Another succinct way of putting this is to say that tau is a stopping time if and only if the stochastic process, whose nth term is the indicator function of the event that tau is less than or equal to n, is adapted. Now, as I noted, we've already seen a number of examples of stopping times. If xn is any adapted stochastic process and b is any measurable subset of the state space, then the hitting time, tb, of the process for that set b is a stopping time. Why is that? We'll just check from the definition. The event that tb is less than or equal to n is exactly the event that there exists a time k less than or equal to n, such that xk is in b. But that's exactly the union over all k less than or equal to n of the event that xk is in b. The event that xk is in b, since xk is an adapted process, is in fk. The fk is form of filtration, so they're increasing, and therefore that union is in fn as desired. Okay, so the first hitting time of a set is a stopping time. How about the last hitting time? The last hitting time, LB, would be the supremum over all n, for which xn is in b. Of course, this might well be infinite, but that's all right. These are allowed to be infinite valued. Now let's compute. The event that LB is less than or equal to n is just the union over all k less than or equal to n of the event that LB equals k. And we can easily describe the event that LB equals k. The last time you hit b being k means that xk is in b, but xk plus 1 is not in b, xk plus 2 is not in b, etc. Now those etceteras are going to give us a headache. This event is in the sigma field generated by xk, xk plus 1, etc. That is typically not going to be in fn for any n. And so usually this LB is not a stopping time. Now, in both of these examples, we can see that it actually would have been more convenient if we only had to check whether the event that tau is equal to n was in the sigma field fn, and in fact, that is enough for any stopping time. If tau is any integer or infinite valued random time, then the following are equivalent. It's a stopping time, which, as we just defined, is the condition that the event that tau is less than or equal to n is in fn for every n. Or we can verify that the event that tau is greater than n, which is the same as the event that tau is greater than or equal to n plus 1 in this discrete setting, is in fn. Or we can just check whether the event that tau is equal to n is in fn for every n. Moreover, in each and every one of these cases, if the condition holds, then it also holds not only for natural numbers n, but when n is equal to infinity. And to be clear, since we're talking about fn, the f infinity in that case is just, as usual, the sigma field generated by the union of all of the fk's, which may or may not be the full sigma field f for the probability space. Now, the proof that these are equivalent follows immediately just from noting that the complement of this set is equal to this set, and that this set is the finite union of these sets. And so using the field, not even sigma field properties, we'll be able to check these implications. And then going from here to here, we just note that this event is the difference between this one and this one at one time step earlier. And I'll let you work out the details if you'd like. Now, to see what happens at n equal infinity, note that the event that tau is less than infinity is the union over all non-negative integers n of the event that tau is less than or equal to n. And each of these is in Fn, so that's in the union of the Fn's, which is contained in F infinity as claimed. And therefore, the event that tau is equal to infinity, which is exactly the complement of that set, is also in F infinity, so F infinity is a field. Now, clearly the event that tau is less than or equal to infinity is, by definition, the whole of omega, and that is in F infinity. And the event that tau is greater than infinity, well, that's just the empty set. So that's also in F infinity, which concludes the proof that all of these conditions also hold with n equal to infinity. Let's think about some more examples. We've seen that hitting times of adapted processes of measurable sets are stopping times. Well, that's the first hitting time. How about the second hitting time, or the trillionth hitting time? Well, in fact, those will be stopping times as well because of the following lemma. If xn is any adapted stochastic process, taking values in a measurable space S, and B is a measurable subset, and if sigma is any stopping time, then the first time after sigma at which the process xn is in B is also a stopping time. So by induction, the second hitting time is a stopping time, as is the third, and so forth. To prove this, we'll use the characterization of stopping times from the last lemma, and we'll look at the event that tau is equal to n. Well, we can just break up the whole space into a partition of all of the possible values of this other stopping time sigma, and so this is the union over all k in n or infinity, because sigma could take value infinity, of the event that tau is equal to n and sigma is equal to k. Now, by the definition of tau, if tau is equal to n, tau is the first time bigger than sigma that something happens. It therefore follows that sigma must be less than tau, which is n in that case. And so this actually reduces to a finite sum. It's the sum k going from 0 up to n minus 1 of the event that tau is n and sigma is k. Well, let's write out explicitly what it means for tau to equal n. So this is the union, k going from 0 up to n minus 1, of the event that sigma equals k intersected with the event that x sigma, which in this case is equal to k plus 1, is in B complement, x k plus 2 is in B complement, and so on, up to xn minus 1, but xn is in B. Well, this event here is in fk plus 1, this event here is in fk plus 2, this is in fn minus 1, and this is in fn. And since sigma is a stopping time, the event that sigma is equal to k is in fk. All of those fk's have k less than or equal to n minus 1, and again, since the filtration is increasing, it follows that this is in fn, which is what we wanted to prove. Now, before we start thinking about how we might use stopping times to analyze stochastic processes, let's just note that we can combine stopping times in all sorts of ways, not just like this one here, to find new stopping times from old ones. So here's a general lemma that we'll use in many different contexts. Suppose I have stopping times sigma, tau, and a whole sequence of stopping times, tau k, k going from 1 up to infinity. Then the minimum of two stopping times is a stopping time. The maximum of two stopping times is a stopping time. The sum of two stopping times is a stopping time. And the limit of a sequence of stopping times is a stopping time. Now, we're making a slightly less generous statement here. If tau k is a sequence of stopping times that is monotone, either non-decreasing or non-increasing, then its limit is a stopping time. We'll prove these all in turn. So let's start with the minimum of two stopping times. Sigma and tau are stopping times. Then the event that the minimum of them is less than or equal to n. Well, the minimum of two numbers is less than or equal to n if and only if at least one of them is less than or equal to n. So this is the union of the event that sigma is less than or equal to n together with the event that tau is less than or equal to n. Each of those is in Fn since sigma and tau are stopping times, and so that's in Fn, showing that that minimum is a stopping time. Similarly, the maximum of two numbers is less than or equal to n if and only if both of them are less than or equal to n. So this is the intersection of the events sigma less than or equal to n and tau less than or equal to n. And that is, again, in Fn since each of those two events is in Fn since sigma and tau are both stopping times. So that shows the min and the max of two stopping times are stopping times. Now for the sum of two stopping times, we can write the event that the sum is equal to n as the union over all possible values of, let's say, sigma, of the event that sigma plus tau equals n and sigma equals k. Since sigma and tau are both non-negative, that union is actually a finite union. That's going to be the union k going from 0 up to n of the event that sigma is equal to k intersected with the event that tau is equal to n minus k. Well, this is in Fk, this is in Fn minus k, since those are both stopping times, and each of those is contained in Fn, and so this is a union of events in Fn, which is then, again, in Fn. And so that shows that the sum is a stopping time. Now finally, suppose that we have a sequence of stopping times that, let's say, increases to some limit, which we'll call tau infinity. Well, first of all, we know that tau infinity is going to be measurable in the same measurable class as the tau k's by the general robustness of measurability under limits. And now let's check whether tau infinity satisfies the condition for being a stopping time. The event that tau infinity is less than or equal to n, how can it be that the limit of an increasing sequence is less than or equal to n? Well, that can only happen since it's increasing if and only if tau k is less than or equal to n for all k. So this event is actually the intersection over the countably many events that tau k is less than or equal to n. Each of those is in Fn, and so this is a countable intersection of events in Fn, which is therefore in Fn. That concludes the proof that an increasing sequence of stopping times has a stopping time limit, and the proof for a decreasing sequence is very similar, concluding the proof. And let me just note right from there that we can then immediately derive that if I have any sequence of stopping times, its supremum is a stopping time. Why is that? Because the supremum is a limit. It's the limit as k goes to infinity of the maximum of the first k. Well, by induction on this, the maximum of the first k is a stopping time. So this is a sequence of stopping times. And as you increase k, this maximum can only increase. So this is a monotone sequence of stopping times. And therefore, by property 2 here, this limit, which is the supremum, is a stopping time. Analogously, the infimum of any sequence of stopping times is a stopping time because that's also a limit. It's the limit as k goes to infinity of the minimum of the first k, and by the same arguments, but with less than or equal to instead of greater than or equal to, that is a stopping time. And moreover, the lim sup and the lim inf are also stopping times, because the lim sup, for example, is the limit, as k goes to infinity, of the supremum over n greater than or equal to k of tau n. Now, for each fixed k, this is a supremum of a sequence of stopping times, and but we proved here that is a stopping time. Moreover, as I increase k, this sequence is a decreasing sequence of stopping times, and therefore, by what we proved here, this lim sup is a stopping time. And a very similar analysis of the lim inf, which is the limit as k goes to infinity of the infimum over n bigger than or equal to k of tau n, shows that that is also a stopping time. Of course, that means that if I have any sequence of stopping times that has a limit, well, that limit will be a lim inf and a lim sup, and therefore will be a stopping time. So, in general, any convergence sequence of stopping times has a stopping time as limit, And more generally, any sequence of stopping times has stopping times as lim_inf and lim_sup.